Hello, my dear students, and welcome to our terminating lecture with the Introduction to Communications course. Today is our final lecture in our course, dealing with what's called the fast Fourier transform, or what's called the FFT. So, please accept my invitation to share my presentation slides and start our final lecture in this module. Okay, I think now you can see my presentation slides, and let's now start opening my laser pointer to start this lecture. Okay, I believe now everything is working fine, and then we can now start our lecture. Okay, as I mentioned, our lecture today is under the title of the fast Fourier transform. I believe this is our third time to deal with the word or to make some usage of the theory implemented by Fourier. We first start our journey with Fourier series, if you remember, one semester ago in your signals and system course. I believe in maybe in the end of this in the end of this module, when you studied what's called the Fourier series. The Fourier series was a way or a theory where you can reach the frequency spectrum of a periodic signal. So your input is a periodic signal in the time domain, and your output is the spectrum. And based on the Fourier series, this spectrum is a discrete harmonic function in the frequency domain. Herein, we have reached our first observation, which is periodicity in one domain cause discreticity in the other domain. So whenever we have a periodic signal in a time domain, we should expect a discrete signal in the frequency domain, which is the case for a Fourier series. Fourier series can be represented, my dear students, in two different ways. Either in the term of a sinusoidal parameter, as you can see in this expression I am highlighting my pointer on, or it can be also in an exponential format with an imaginary coefficient. This is actually a very simple trigonometrical way, because you simply know that this exponential with an imaginary coefficient can be expanded into, can be expanded into cosine and sine signal. So this is just a trigonometrical formatting of the equation, either in terms of a sinusoidal coefficient an, Pn, or in terms of an exponential coefficient Cn. So this is how Fourier series works. Then we transfer by the starting of this module in our lecture number 1, if you remember, my dear students, we transfer to deal with what's called the Fourier transform. Herein I name it the continuous Fourier transform. Actually, by this, or by the time we had this lecture, we were only dealing with a continuous signal. So I don't need to say it's continuous, because we only know continuous. But after reaching the sampling theory, we know now that signals in time domain can be either continuous or discrete. And as far as you are implementing what's called the integration operator, which is an analog operator, by the way, so your signal here, this signal should be a continuous. That's why we call now this Fourier transform as a continuous Fourier transform. So in a continuous Fourier transform, now your signal is no longer periodic. It's an aperiodic signal. And you can use this integral operator in order to get what's called the x of f over the signal in the frequency domain. And of course, we have what's called the inverse Fourier transform, where you can return back the signal from the frequency domain back to the time domain. So this is a Fourier transform. Now the question is, what if we would like to make a Fourier transform, but in this time your Fourier transform is for a digital or for a discrete signal? That's why we have to play this lecture after the digitalization lecture, not before. Maybe your first question is why we are terminating our module with the fast Fourier transform. As far as this is a Fourier transform, so then we should have it in the first portion of the course where we will deal with Fourier transform analysis, system domain analysis, and all this stuff. However, the fast Fourier transform, or what's called the discrete Fourier transform, is mainly seeded with a digital signal. That's why you should first have an overview on the digitalization or the discretization process. Then you should start dealing with the fast Fourier transform. Okay, so our challenge, our target now, my dear student, is to have a discrete form for the digitalized signal. Okay, so back to the first observation in this lecture from the Fourier series. Discretization in one domain cause periodicity in the other domain and vice versa. So as far as you are going to put here a discretized signal in the time domain, you should expect here a periodic signal in the frequency domain. Great. And what if your input is also a periodic? So your new input here will not only be a discrete, it's a discrete and a periodic signal. So as far as the input is discrete, then the output is periodic. And as far as the input is periodic, again, the output is discrete. So in the DFT, our input, which we will call it later on x of n or x of any dummy integer. So let's say it x of n. So whenever your input is a discrete and a periodic, you should expect an output in the frequency domain, which is also discrete and periodic. And this is the discretization of the Fourier transform, or what's called the discrete Fourier transform, or the DFT. So let's now start to discretize this equation. Now let me please share my whiteboard screen. Sorry for being late. Yeah, this is my whiteboard screen. So let's now share my whiteboard screen and start this process. Okay, so let me first start with some sort of a very quick flashback on what is the difference between an analog and a discrete signal. Please remember that generally discretization means discretization in the x-axis, which is the time domain, and also discretization in the y-axis, which is the amplitude. However, of course, if you remember, discretization in the x-axis is called sampling, and discretization in the y-axis is called quantization. However, whenever we are dealing with the Fourier transform, we are only concerned about time. So we will not think about the quantization process. We will deal only with the discretization with respect to the time process. So generally speaking, you have a signal in the time domain, which called x of t. And this signal this is a t and this is x of t, of course. And this is, of course, a continuous or an analog signal, generally speaking. So that's perfect. Now, you need to discretize the signal in the time domain. So you go to do what's called the sampling process. I believe you remember the sampling process, or what's called the Nyquist rate, the Nyquist sampling rate, which is at least double the frequency of the signal. So if you are going to make some sort of discretization, my dear student, you will have some, okay, so you will have some samples like that. This delta Dirac samples are the sampling process. Here we assume an ideal sampling, if you remember. And if you remember, my dear student, the output of this, or the output of the sampling process, we call it x of nts, where ts is a sampling time, I mean the time between each two successive sampling, and n is just an integer starting from zero reaching to the whatever n is. So this is simply the analog version or the continuous version and the discrete version in the time domain. Now, if I would like to make some sort of a Fourier transform, if I would like to observe the frequency spectrum of this analog signal, I will use what's called the Fourier transform, which is as follows: x of f equals to integration from negative infinity to infinity for what? So it's an integration from negative infinity to infinity for what? For x of t e to the power negative 2 pi ft dt. This is simply what's called Fourier transform. It's an integration with respect to time. That's why t here is what's called a dummy variable. So what you will get from this integration is something in terms of frequency. Now, what we are seeking for is having some sort of analogy, having another formula instead of these formula, but with having an input x of n instead of x of t. Our input now, my dear students, is not a continuous signal in time, it's a discrete signal in time. So instead of t and f, we should have new variables, because simply now we don't have t and f. T is a continuous time spectrum and f is a continuous frequency spectrum. So we need to replace them by a discrete version of t and f. So let's call it n and k. So let's say that t is discretized into n and f is discretized into k. So this is just to have an integer discrete format of the axis. So n represents 0, 1, 2, and 3. What is 0, 1, 2, and 3? It's 0 ts, 1 ts, 2 ts, 3 ts, and so on. And k represent 0, 1, 2, and 3 again, but it's 0 fs, 1 fs, 2 fs, and so on, where ts is the sampling time, fs is the sampling frequency. That's all. Okay, so now we have x of n and x of k. And you can understand that now x of n is something discrete in the time and x of k is something discrete in the frequency. Okay, perfect. So x of k is equals to, now it's integration. The integration is an analog summation process. You know, I believe you know this perfectly from your mathematics module. And the discretized version of the integration is the summation. So summation and the integrations are equivalent, but integration is an in continuous axis and summation is an discrete axis. So you have here summation instead of integration. Okay. Then you have your x of n perfectly. And you have this exponential, which is e power minus j2 pi. And then we have to stop. Perfect. Now we have f and t. So we should have some replacement for f of t. So let's think in a very easy manner. Let's think in a very easy manner. Okay, so how can we do it? So let's start to make replacements. This f, which is a frequency, is now replaced with k, because now f is the k. And this t, which is the time, which is the dummy variable is in the integration, is now replaced with n. So you have e power minus j 2 pi n k. But we are still missing a very important parameter, which is the limit for this summation. So from the first principle, you will say, okay, our integration is from negative infinity to infinity. So we have a summation from negative infinity to infinity. But we have to remember that we say that in this discretization version, we assume two issues, two very important issues. That our new time domain signal is discrete. That's why we replace the t with n. And also we assume that it's also periodic. And this is an obligatory assumption. Why this is an obligatory assumption? Because in order to have a discrete frequency domain, your time domain must be periodic. Your time domain must be periodic, because now you say that I have a discrete frequency domain. So you don't need to make an integration from negative infinity to infinity as far as the signal is a periodic signal. What you are going to do simply, my dear student, is to make a summation over one period. Herein, we can assume our period is extending from n is equals to 0 to n minus 1. So you have n points within the period. So for example, let's say that this is a period and you take 4 samples in the period. So you have from 0 to 3. This is your samples. So that's why we integrate here from 0 to n minus 1. And one mathematical correction is needed, is that you have to normalize here over the period, because when you are doing this 2 pi equivalent to one period on the angular domain. So you have to normalize it over your sample. So you have to have 2 pi over n. So this is the discretized version of the Fourier transform, or what we call the DFT, the discrete Fourier transform. The discrete Fourier transform is the discrete version of the Fourier transform where we have our input is discrete and periodic, and our output again is discrete and also periodic. Okay, let me now return back to my presentation slides. Okay. Perfect. Now we have the discretized version of the Fourier transform, which is the DFT, as you can see here. This is the discretized version of the Fourier transform, and this is the discretized version of the inverse Fourier transform. So you can do the same exercise to convert the inverse Fourier transform in its continuous format, which is this formula, to get this formula. Again, as you can see, this is x of n, which is your input, and this is x of k, which is your output. Okay, that's perfect. Herein, you can ask me a question. Why you are titling this lecture with fast Fourier transform, not a DFT, not a discrete Fourier transform? We are doing a discrete Fourier transform, not a fast Fourier transform. Actually, up till now, we didn't hear about the fast Fourier transform. So, why we call it a discrete Fourier transform? Why we call it a fast Fourier transform, or why we use it, the fast Fourier transform, or why in the MATLAB, whenever you did your project, you use the command FFT, not DFT. Okay, simply the answer is in this line. The main issue related to the DFT, the main drawback, let me say, related to the DFT is the high or the complicated or the sophisticated computational resources or operations needed. So in order to perform a DFT process, you need to make n square complex multiplication and n times n minus 1 complex addition. And of course, whenever you are dealing with an embedded system who is performing this task, I believe you are genius with that. So you know that delay will cost money. So you have to make a process for an MP3 file or for an image or for a video, MP4 video or whatever. So you have to increase the number of samples. We know that. We know that we should increase the number of samples to have this Nyquist rate. So n is going to be increased. And then whenever you have a high n, then you will have a high complexity in the system, and then you will have more and more delay. So this is a problem dealing with the fast Fourier, so is a discrete Fourier transform. Okay, let's examine it by ourselves. Let's do a very simple example. Let's do the most simple example where we have n is equals to 4. We only have our 4 samples. So let's examine, I mean here for n capital, of course. So let's examine what if n is equals to 4, and then we are going to, we have a question. I give you a question in the final exam. Please make a discrete Fourier transform for this signal. So let's see what will happen. Okay, perfect. Oh. Now our example is we have okay, perfect. Okay, now our example is we have x power n equals to, for example, x1, x2, x3, and x4. These are the 4 samples in the time domain. Perfect. And then we would like to calculate the xk, or x of k, which is the equivalent samples in the frequency domain. Okay, so let's first start writing the equation. X of k is equals to summation. Now the summation will be from n equals 0 to n equal 3 for x of n e power minus j 2 pi n small k over 3. I'm sorry, over 4. This is the what's called the n capital, or the samples per period. Okay, so let's first start to expand this summation. So let's say x of k equals 2. So first for n equals 0, I'm sorry, it's better to make it 0. That's right. 1, 2, and 3, just to be consistent with the numbering over the summation. So of course these are just a dummy sample, so you can call it whatever you want. So x of 0 will be x0 e power minus j 2 pi n is equals to 0 times k over 3. This is plus n is n equals 1, so you have x1 e power minus j 2 pi 1k over, I'm sorry, this is 4 and this is 4, I'm sorry, plus, let's have the fourth term. Okay, let's have the third term. I'm sorry, not the fourth. Let's have the third term. So its third term will be x2 e power minus 2 pi 2k over 4. And finally, the third term, x3 e power minus j 2 pi 3k over 4. These are the four terms. Now you should substitute 4 times in order to get your 4 outputs. When k is equals to 0, then you will substitute here with k equals 0, then k equals 1, then k equals 2, and then k equals 3. Then you will have the 4 terms for x of k. This is simply what you are going to do. Of course, here we have a complex multiplication process, as you can see, because generally you can have an x of 0 or x of 1 is a complex function. So this is a complex function, of course. So you have a multiplications, as you can see, 4 multiplications, and you have 4 summation process. So that's why this is a complicated somehow process. So what should we do, or how we can make this process more simple? In order to study how we can make this process more simple, let's try first to think about what is in our hand, what is constant. This x0, x1, x2, and x3 are random inputs. I mean, it's an unknown input. It's dependent on the message. I cannot expect how should x0 and x1 and x2 and x3 will look like. This is dependent on the message. But these coefficients are constant. These are general and constant coefficients. So you can now think about the coefficient because you can tune the coefficient, but you have no access for the message. So, for example, the first coefficient is simply equals to 1 all over the time, because whenever you have an n equals 0, this will be 1. That's perfect. And also, let's have a look here. This coefficient is 2 times 2 is equals to 4. So this is e power minus j pi k. E power minus j pi k. And this is e power minus j 2 pi k. And this is e power minus j 3 pi k. So as you can see here, sorry, this is 3 pi over 4k. So as you can see here, we have the term e power minus j somehow is a common factor in all these 3 parameters. So you can simply consider e power minus jk here, or e power k at least here, as a common factor. Let's see. So x of k equals 2. X of 0 will be multiplied by 1 because it's e power 0, which is 1. Okay. Plus. Now let's start to think if we consider e power k as a common factor. So, or let's make it e power minus k because we have minus all the way. So we have x power 1, or x1, I'm sorry, not x power 1, x1. x1 multiplied by e power j. We have, let's return to this paper. We have now, we get k, e minus k common factor. So we have 2 pi over 4. So we have pi over 2. plus we have again x2. X2 is equals to, sorry, x2 multiplied by, let's see it here. We have e power minus, okay, e power minus k is outside, so we have e power 4 pi over 4, so we have e power j pi, e power j pi plus we have now e power minus j k again outside as common factor, so we have e power 2 times 3 is this is 6, 6 over 4, which is 2 over 3 pi. So this is somehow mathematically a bit simpler than the original format, which is this big, sophisticated format. So now, what should we do? The next is, let's examine these terms. These are deterministic terms because, as you know, my dear students, e power jx is equals to cosine x minus j sine x. So you can determine these values. Let's start, for example, with e power minus j pi over 2. E power minus j pi over 2 is simply cosine pi over 2 minus j sine pi over 2. Cosine pi over 2 is 0 and sine pi over 2 is 1. So this is minus j. Then let's go here. E power minus j, e power j pi. E power j pi is simply cosine pi, which is -1, and sine by 0. So this is -1. And similarly, here you will find that this is j. So you can rewrite the equation in this format. X of k equals x of 0 plus e power minus k pi j x1, it's minus j, yeah, x1 minus x2 plus j x3. Again, you can do a more and a more simplification. If you examine now this equation, you will find that you have two types of these x of k terms. You have a pure real and you have a pure imaginary. X of 0 and x of 2 are pure real functions, but x of 1 and x of 3 are pure imaginary functions. By the way, this is not something by chance. Here, the distinguishing is basically based on even and odd functions. Even terms are real, and odd terms are imaginary. So you can classify or you can distinguish now these terms as follows. So let's say it. Again, x of k equals x of 0 minus e power minus k x of 2. And here we have plus, or plus, yes, j so we have now the odd terms are represented in an imaginary format. So we have so we have minus x2, sorry, minus x1 plus x3 here e power minus j e power minus k. So as you can see, this is a simplest format in order to perform this DFT operation. Now, what we are going to do is that we are going to make this simplification somehow in a generic form, in a generic format, what we call the fast Fourier transform. So back to our presentation slides, and let's again open the pointer. Here, this is a standard, let me say, the standard format for the discrete Fourier transform. And again, the problem is that huge number of multiplication and addition implemented in order to perform this DFT. And this is the steps we just did together. And now this is the new model, or what we call the fast Fourier transform. The fast Fourier transform is an enhanced simplified algorithm where you can perform DFT by separating the even terms and the odd terms and then performing the DFT separately for the even stream and the odd stream using what we will call the butterfly model. It is simply called a butterfly model because what you are doing is some sort of a cross multiplication as in the butterfly. So, for example, when we are dealing with the even term, here what we call the g of k, we separate the x of k into g of k and h of k, where g of k represents the even part and h of k represents the odd part. So whenever we are doing this even and odd term, we are doing this some sort of a butterfly. Let me return back to my white paper in order to discuss this this uh, butterfly model. Okay, so let's now deal with the g of k, or the even terms, which is this terms. This represents the g of k, or the Fourier transform, the discrete Fourier transform, due to the even terms. Now we have two output of this. We have for x of 1 and x of 2. I mean here by substituting 1 and 2, or sorry, I'm sorry, 0 and 2, the even terms in the k. So for x equals for x equal for k equals 0, you will get k0 minus k2. For k for k equals 2, you will get k0 minus e power minus 2 k2. So what you can, or you can convert this into something like that. Here x0 and x2, or what we call, I'm sorry, x0 and x2, these are the time domain, and here x of 0 and here x of 2. And here you have multiplication factor of 1, and here you have a multiplication factor or minus 1 and e power minus 2k. So that's why we call this the butterfly model. So Let's return back to the presentation slides. This butterfly model is simply represented here. So you have two inputs, which may be the even terms or the odd term. You have some weighting or multiplication factor, and you have two outputs. Similarly, you can do the same for the odd terms. So you have this butterfly model in order to perform the DFT performance per even track and per odd track. And you can extend this not only for 4 point, which is our example, but for even more. Let me also describe to you this W term. I believe this appears here. Yeah, this is W term. This W term, my dear students, is just equivalent to the exponential. So instead of saying e power minus j 2 pi n k k over n, we say this is W of n k over n. So simply, just to make life more easy, okay, so generally we have this exponential term, which is e power minus j 2 pi n small k over n capital. So this is simply equivalent to w n k over n. So for example, when I say w uh, k over 3, this is simply mean e power minus, or it's not for 3, so it's 4, e power minus j 2 pi k over 4. So this is simply what is implemented for this multiplication factor. So you can simply write this here. Let me return back to the slides. So you can simply write this butterfly model to represent whatever you want to represent in this multiplication between each two terms. And accordingly, you can expand this for 8 FFT, for 16, 32, 128, 256, 512 FFT using this model. It's the same model, my dear students. Start by dividing into a pair of couples. Each two terms will have a DFT together, and then the output will be DFT with the next stage, and then with the third stage, and so on. So you need n stages, or I will not call it n because we already use n. Let's call it L. You need L stages, where L is simply 2 power the number of points. So if you have 8, then the FFT will be implemented on the 3 stages. If you have 16, then the FFT will be implemented onto 4 stages, and so on. Usually, I'm not so interested in dealing into deep mathematics of FFTs, because simply you have a very powerful tools that can implement the FFTs automatically. This may be a MATLAB code or Python or whatever it is. In all these programming languages, you just need to type one command to perform the FFT. So it's not a matter of mathematics, my dear students, in order to understand. It's a matter of understanding, to know the number of points, to know the nature of the signal, to know the nature of the output, to know the sampling rate, the minimum sampling rate, which is the Nyquist rate, in order to perform digitalization or discretization. So, my dear students, again, I will not focus in my exam in order to have an example of stream of bits and say, okay, go to do this multiplication, complex multiplication steps in order to perform the DFT or the FFT. No, our applications will be, or our examples will be more toward conceptual. Yeah, okay, then this is the final slide in our module. As I told you, maybe in the beginning of this module, I told you that this is an intermediate module. You have already taught the uh, signals and system course in your second semester in the in your second year after prep, and this is just a linking course in order to introduce your next topic that will be delivered in the next semester, inshallah. Fortunately, I will not be the module leader. You will have more expert module leader with you in order to deliver this digital signal processing course. I believe this is one of the most important courses and the most potential courses for you as a computer engineering. So I hope that you can make use of what you have learned in this course, mainly the last part, the last portion of this course, dealing with the discrete Fourier transform and also the digitalization port, dealing with digital modulation and sampling and quantization and encoding. That can be useful with your next step in the DSP course. Maybe also you will have more advanced courses in the year four. I mean, I believe you have an optional course with image processing that also can be that also FFT can be utilized in. So thank you very much for your attendance and for your collaboration and participation along 12 successive lectures in this module. I hope, actually, for myself, I enjoyed the course. I enjoyed delivering these signals and the communication part. But what is more important for me is that you enjoy yourself, you enjoy this course. For me, it was some sort of a new challenge to deal with you at a computer engineering, as a computer engineering student or in a computer engineering program, or a promising computer engineers, in order to understand new concepts related to introduction to communication module. As I mentioned, we divided our course into three portions. We deal with signals and systems in the beginning of the course. Then we transfer to the analog communication techniques as a bridge to the digital modulation techniques, the digitalization, the discretization, and finally the TFT. Now, the fast Fourier transform is considered the termination station for our journey. It's a long journey. I hope that we did our best to make you satisfied with this content. And I hope that by 2 or 3 or 4 years from now, after your graduation, you make use from this information where we dedicate 12 weeks to learn. Thank you very much. Thank you for your understanding, for your collaboration, even for your participation, and with your dealing with the, let me say, the unstable conditions related to the COVID-19. The course was nearly fully online, but I believe that your attendance level was always above 70%, which actually usually, or which always push us toward better and better understand delivery and dedication to keep you always engaged with our module. Thank you very much for your effort, and maybe this will be my first and my last course to be delivered to you. So most probably I will not join you again in any other courses. So hope that you have a very successful semester, a very successful year toward your graduation year, inshallah. Thank you very much. Finally, thank you very much for your participation, and maybe see you after your graduation, inshallah. Thank you very much, and bye bye.